Peres, talking on unpredictable paths and percolation.
Thanks, David. In this talk, I want to give you a survey of this topic of paths that are unpredictable or hard to predict, and how they are used. I'll only be able to mention a few of the applications. There are various sophisticated ones I won't get to. So we all know and recall that simple random walk in Z3 or ZD for higher D is transient, and there are myriads proofs of that, each with its own advantages. More sophisticated fact that was maybe the start of this journey for me was the result of Grimmett, Kesten, and Zhang from the early 90s. And what they showed is that if you do supercritical percolation, so for P bigger than PC of ZD, here D greater or equal than 3, the infinite cluster, so we know there is a unique infinite cluster. So it's almost surely a transient graph. So in other words, you pick the infinite cluster, and now you put a particle on it, and it's doing a simple random walk on this cluster, and this is a transient process. So transient Markov chain, it goes off to infinity. And their proof used a quite advanced understanding of percolation that was obtained at that time, and there is a basic philosophy that underlies that, and then many later investigations, and is still open, namely that for groups, or more generally for transitive graphs, qualitative properties of the group are inherited by the supercritical percolation cluster. Many properties, and many are proved, and many are still conjectured. For instance, it's still open whether in any group, if the random walk has positive speed, is it true for random walk on the infinite cluster? For transients, the situation is better understood now, and that's part of the story I want to tell. Before getting into the percolation clusters, I want to illustrate the method of random paths that we'll be using by the simple case of transients in Z3. So here is one of the many approaches, one that will be the basis of the further generalizations. So find a probability measure mu on paths, but let me make them oriented paths. Okay, so these are paths that go up in one of the coordinates at every step, oriented paths in Z3. Such that if we sum over all edges in the lattice, the measure of the paths phi, so we take an oriented edge, and we look what is the measure of the path that goes through this edge, and suppose this is finite, then of course this implies transients. So this is a criterion that's been discovered several times. In some places it's called Terry-Lyons criterion, because there is a 1984 paper in Annals of Probability where it's stated in slightly different form. Instead of talking about measures on paths, it's stated that there is a flow from the origin to infinity, So here I have oriented paths. In his theorem, you have a flow from the origin to infinity, meaning at every node, so you have an edge function, a function on edges, so that at every node, the incoming flow equals the total outgoing flow. So there's no requirement for this flow to be oriented. And if this flow is square summable, finite energy, then the graph is transient. This also follows from the electrical network theory, where the minimum of this, if you take infimum of the sum of squares, you get the resistance from the origin to infinity, and finite resistance is a criterion for transience. So this is the way I stated it here, insisting that the path is oriented. It's a sufficient condition. Okay, so square summability of a flow. So assume almost all of you know it, and otherwise let's just take this as our proxy for transients. We want this sum of squares to be finite. Well, where do we get such a measure? There are many ways. So one way which I like because of the historical naming is consider Polya's urn. So let's start, instead of the origin, start at the point 1, 1, 1, and think of it as a situation in Polya's urn. So you have one red ball, one black ball, and one blue ball. And at each time, you pick a ball, look at its color, and return it together with another ball of the same color, and keep going. So each time, pull out the ball and return it with a ball of the same color. And as you track the history of this process, you start at 1, 1, 1, and you keep going, of course, in an oriented path. Each time you add a ball of one of the colors. So if you track the history of the process, you get an oriented path. Now, it's a classical and easy to check property of Polya's urn, that when you get to level n, to vectors with total sum n, the distribution is uniform over all vectors of positive integers that of length, triples of positive integers that add up to n. And there are order n squared such vectors. So what you'll get, so if we partition all the edges according to their distance from the origin, each one we have, so I'm going to ignore constants, we're going to get n squared such edges at distance n from the origin in Z3, because you just have to write n as a sum of three integers, three positive integers. There are about n squared ways to do that. Each one will get a measure of 1 over n squared, because the Polyan urn is uniform over these, again, ignoring constants. And we have to take this measure and square it. So when we sum this, we're just summing 1 over n squared, so this is finite. So Polya's urn proves for you Polya's theorem on transients of Z3. And but this is just one way to get such a measure. And a simpler way is as follows. Just go from the origin and choose a random direction. That is, look at the unit sphere, maybe in the positive 1/8 of the unit sphere. So, and just choose a point there at random. Right? So we take the sphere, we choose a direction at random, and we just take an infinite ray through that point. Well, that's not in the lattice, but just choose some kind of closest approximation to that ray in the lattice. Okay, so this is a random path that you get just by rounding the random ray. And when you do that, if you have an edge at distance n from the origin, what's the chance that you'll pass through it? Well, it's just a question of what angle, the rays that, so here's an edge, and you want to know what's the chance the path will go through it. Well, for the path to go through it, the ray should come within distance 1 or 3 of this edge, right? Some constant distance from this edge. But this edge is a distance n away, and the total angle of these rays is easy to see. It's constant over n squared. So just this method, just choose a random direction. Okay. Now, all right. Now, when we want to go to the infinite cluster, we can't quite do it that way. So we still would like maybe a measure on edges in the infinite, a flow on edges in the infinite cluster, which is where summable, but the infinite cluster is a complicated object. So what we'd like instead is to find a measure on the full lattice, which will give us such a path. But the condition for this measure is more restrictive. So we say that the measure mu, so mu is, again, a probability measure on some kind of oriented paths from the origin. So we say that this measure satisfies the property EIT. So this is exponential intersection tails with parameter theta. If, when we take two independent paths, phi and psi, according to this measure, the probability that they will intersect in k edges or more than k edges should decay exponentially. So it should decay like constant theta to the k. So here theta is some number less than 1. Okay, so a measure mu has this property, exponential intersection tails with parameter theta, if when we take two independent paths, notice that this says that when we take two independent paths, the expected number of intersections is bounded. Here, instead of just bounding the expected number, we want exponential tails. And then one theorem from this 98 paper, well, it was done in 95, but appeared in 98, with Beniamini and Pimentel, is that if we have this EIT exponential intersection tails property, this implies that for all p bigger than theta, the infinite cluster, so right, the infinite cluster with parameter p is transient. And so this, the way I'm stating it, it's contained in the Grimmett, Kesten and Zhang theorem, but this gives something stronger also, because this is also true for oriented percolation. So you can do ordinary percolation or oriented percolation, where so you only look at the cluster composed of unions of oriented paths, and for p large enough, so you get the transients. Actually, to recover the original Grimmett, Kesten and Zhang theorem, you have to do a little more here, because this will prove it for large enough p, and to drive all the way down to pc, you need a further renormalization argument that I'm not going to get into, but it is explained in the paper, in that old paper. Okay. So what's the idea here? Well, there are two things I have to say. One is, how can we get such a measure? We saw measures with this property, but that property over there is stronger. Certainly taking a random line is not going to do it. But I want to emphasize that this measure here is not a measure on paths in the cluster. It's a measure on paths in the whole graph, which has implication on the cluster. Okay, it's a measure on paths in all of ZD. So why does that imply that the cluster is transient? So first, it's useful to note that this implies indeed that P is bigger than PC. So that, right, any P, so theta is in fact at least PC. And the reason is that if you look at a random variable which essentially counts open paths, but with weight mu. So let Zn be the mu measure of the paths phi, so that phi n is open. So by phi n, I mean I truncate phi to the first n edges. Okay, now That's right. So suppose that mu has the EIT property, and define first Zn to be this variable. What can we say about, so mu is a fixed measure, but phi n open refers to the p percolation. So this is in open in percolation with parameter p. So the first n edges of phi. Now, what's the expectation of Zn? What's the probability that a particular path of length n is open? P to the n. And so the expectation of this by Fubini will just be p to the n. What's the second moment of Zn? Right, so you have to take two paths, phi and psi, and integrate the indicator that phi is open and also psi is open. So when you think about this, the important thing is how much phi and psi intersect. So let's call that number k. We know that the probability that phi and psi intersect in k edges is bounded by a constant theta to the k. Now, if they intersect in exactly k edges, then the total number of edges in phi and psi is just 2n minus k, right? 2n minus the overlap. So we need 2n minus k edges to be open. So if we look at the crucial ratio, so now what can we say about the probability that Zn is positive? It's always at least the first moment squared divided by the second moment, right? That's second moment inequality. Right now, when you do that, the p to the 2n cancels, right? And you'll get that this is bigger than the sum over all k. So here the sum, of course, is restricted to n, k at most n, but we can bound this below by the sum over all k of theta to the k, p to the minus k. And the point is, this is uniformly positive for all n. Okay, so the probability we reach distance n is uniformly positive. So with positive probability, the origin is so in taking intersection over all n, with positive probability, the origin is in infinite cluster, so we have percolation. But unlike other proofs of percolation, the usual ones using duality, this one immediately gives us also transients of the cluster. And the reason is you can just define a flow. So let's find a flow on the cluster up to distance n with a bounded energy that doesn't depend on n. Once we do that, again, we can take a limit and get a flow of finite energy on the whole cluster. And what you do is define the flow through an edge E is just the mu measure. Mu has that EIT property. The mu measure of the paths phi that are such that phi n is open and E belongs to phi n. Okay, so this is an edge E within distance at most n from the origin. Okay, an oriented edge within distance. And this defines a flow on these edges. So I'm not trying to define the flow on the whole lattice, just on the edges going to distance n. And we're going to bound the energy of that flow. If that is uniformly bounded, then just passing to a limit will give us a flow on the whole lattice. Or you could just say that this bounds the resistance. Bounding this energy will bound the resistance from the origin to a distance n. And then if you compute the sum over all the oriented edges up to distance n of Fne squared, what you'll see using the same logic, so you have to, so again you get the double integral over path mu and path phi and psi, and again the important thing is the number of edges that they intersect. So you'll get something. So we'll actually want to normalize this. So take this and normalize by p to the n. And then when you bound the energy of this flow, you'll get this kind of sum we had before with an extra factor of k, because if the paths have k intersections, then each of these edges is one possible candidate for the edge E here. So I'm going to, in view of time, not go through this bound. You can, again, think about it in a few minutes, or it's just interchanging the order of integration and summation in this sum gives you this. And of course, again, if P is bigger than theta, this is uniformly bounded, which will give you a uniformly bounded energy for this flow. And on the other hand, the division by p to the n here guarantees that the total mass of this flow isn't going to 0. That's basically the calculation we did before. So this flow, even if it's not a unit flow, it's some flow that's not disappearing as n goes to infinity. So this can be used to prove transients. Okay, so how does one construct such measures? Measures with EIT theta. Well, in dimension 4 and higher, this is easy and was already done by Cox and Durrett in 91 without all the fancy definitions, but they had the paths. And it's a very nice paper, and they prove a theorem there. They estimate the critical probability for oriented percolation. They do it using this type of second moment argument with a suitable measure mu, which is very simple. And they thank Harry Kesten for giving them the idea for proving their main theorem. And what is the idea? The measure mu is the simplest you could think of, uniform measure on oriented paths, meaning you just take an oriented random walk. You start from the origin. You have d possible steps you could take. Just decide which coordinate you want to increase. You choose one uniformly, and you keep going. Okay, so this is just a random walk in ZD obtained by choosing one of the d standard basis vectors at each step uniformly and just going with that. And so for d at least 4, a uniform oriented paths in the sense I told you before have EIT theta. And the proof is really easy. What do we need to check? We need to take two uniform oriented paths and check the number of intersections they can have. Now, we have to count the number of edge intersections, but let's be generous and count the number of vertex intersections. That's bigger. Now, two oriented paths to intersect, they must have, it means that their difference at time n is 0. So what we have to bound is the probability that the number of n, so that phi n minus, so I'll write phi of n minus psi of n is 0. So now I think of this as the nth vertex. So we have to bound the probability, the probability that this number is greater than k. But what is, if we take the difference of two oriented walks, this itself is a random walk in the lattice. It's no longer oriented, but it's one dimension lower because it's restricted to the hyperplane where the sum of the coordinates is 0. It's easy to check that that's the only restriction. So this walk is really a d minus 1 dimensional walk. If I look at phi n minus psi n, this is performing some walk on this hyperplane where the sum of the coordinates is 0. And so if d is at least 4, this is at least a 3-dimensional walk, which itself is transient. So we're asking for this transient process to revisit 0 k times. Well, it's just the return probability for a transient process to the power k. So this is indeed behaving like some theta to the k, where theta is less than 1. Now, this technique really fails for 3 dimensions. And if you try to examine why it fails, it's because these uniform-oriented paths only use a small portion of the lattice. They stay rather close to the diagonal. So after n steps, these random-oriented paths that we think of as uniform, but they're really staying in some square root tube around the diagonal. They only get to distance about square root n from the diagonal. So they're not really exploring the whole space. So in order to prove this in d equals 3, we have to make more efficient use of space. And thinking about how to do that led us to a question of some independent interest already in 1 dimension. So so let me make a definition. So suppose Sj is a nearest neighbor process in Z. So Sj plus 1 minus Sj, let's make it exactly 1. And then the predictability profile. So I want to say how predictable is this process, and it's defined as follows. It's the supremum over x, n, and I'll say history of the probability that Sn plus k equals x given, given S0 up to Sn. So I have a nearest neighbor process. It only moves plus minus 1. And let's say, given that I know the whole history until time n, how well can I predict where the process will be at time n plus k? This is the predictability profile. And, well, simple random walk has predictability profile of order constant over root k. And at first you think, can I get something which is less predictable than simple random walk? Simple random walk looks, the most random. But that's misleading. The steps are the most random, but that creates a lot of cancellation. So the locations are not the most random. So in the original paper, we constructed predictability profiles of the form k to the minus alpha for any alpha less than 1. And this was refined in the paper that appeared shortly after by Hegstrom and Mossel, and they showed that you can get a log k to the 2 plus epsilon over k. I'm sorry, log k to the 1 plus epsilon over k for any epsilon. And in fact, they gave an exact condition. So you can get the predictability profile of the form f of k over k if and only if the sum of 1 over k f of k is finite. So I should say more carefully, they showed if, And then Hoffman showed that this condition is sharp. So Hegstrom and Mossel sharpened our original theorem, giving two distinct constructions that got to this kind of predictability profile, and more precisely, they could get anything like that, provided this sum is finite. In the original paper, we knew that this is possible, and it's impossible to get constant over k, but they showed this, and a later paper by Hoffman in analysis of probability showed this condition is sharp. Okay, so we know exactly what predictability profiles are possible. Now, from these unpredictable paths, one then can construct a process with EIT, and I'll just so if you have unpredictable paths, by which I mean something. So something non-trivial here is the moment alpha is bigger than half, then we're already playing a non-trivial game. Okay? So how does the unpredictable path lead to EIT? So first, change the path. Instead of having steps plus minus 1, make steps 0, 1. So that's just, let's take Wn to be n plus Sn over 2. Let's take Wn sharp to be an independent copy. And then I'm going to define a path in Z3 as follows. So gamma n looks like this. Wn over 2 lower integer part. Wn over 2 upper integer part. And then n minus these two things. Okay, now, what is the game here? So, what this means is, depending on whether n is odd or even, either this coordinate or this coordinate has a chance to increase by 1. Okay? And whether it increases by 1 or not is governed by this unpredictable path. Okay? So here I take lower integer part, here I take upper integer part. So when I go from n to n plus 1, only one of these has a chance to change, depending on the parity of n. Okay?
So what, a three-dimensional one?
Yes, this is the third coordinate. Thank you. Sorry. Right, I want a three-dimensional walk, which is oriented, so at time n, it will be exactly a distance n from the origin. So at every step, exactly one of these three coordinates will go up. Thanks for catching that. What? And there are some sharps, boy. Thank you. At least I know some people are noticing. Yes, another typo. What? I'm sorry?
The first sharp should be on the third entry.
What? No, I think this is fine. So, okay. So at every time, exactly one of these coordinates will increase by 1. No. Okay. At most, one of these can increase when I go from n to n plus 1. Okay? And if they both don't increase, then this third one will increase. Okay? So this will give us an oriented path. And if you think what's the predictability profile of this, it's basically, so the predictability profile of gamma at k is basically the predictability profile of S at k over 2 quantity squared. So if the original predictability profile is square summable, then gamma has a gamma, which is now a path in Z3, has predictability. But the definition of predictability profile, I defined it for nearest neighbor, but it's, I mean, the same definition makes sense in any space. And so the moment alpha here is bigger than a half, you get that gamma has a summable predictability profile. And summable predictability profile easily seen to be is easily seen to imply EIT. Because if the expected number of intersections of so from summability you get that the expected number of intersections to the future is finite. In particular, after some number of steps, say 100, the expected number of intersections is less than a half. So but even if there is another intersection after distance 100, then you condition on the whole path and repeat. So just by iteration argument, it's easy to see. And again, there's, I won't do this in more detail, that summable predictability profile implies EIT. Okay? And so that's how we get a process with EIT in 3 dimensions, if we have a process which is unpredictable. Now, how does one get an unpredictable process? So, so it's easier. So there are several constructions. It's easier to present. So we had one in the original paper, which is a little more complicated. This was simplified and improved by Hegstrom and Mossen, and let me tell you the simplified version. So this is connected to the problem of reconstruction on trees, Ising model on trees, and it goes as follows. So take a binary tree and put here a plus or a minus equally likely, and then along every edge, say we put a plus here, you flip with probability epsilon. So if we have here some value s, here we have s with probability 1 minus epsilon, and minus s with probability epsilon. So s is a sign. Okay, so this is how we go from a father to a son, or from a parent to a child, just by flipping with probability epsilon. So it's the binary symmetric channel with error probability epsilon, or it's a mutation model. And so you do this for some very long height h, and then you get some random but quite correlated spins on the boundary. So really you should think of epsilon here as quite small. And the crucial condition, you want 1 minus 2 epsilon to be bigger than 1 over square root 2 to get something interesting. And then you just, the process is obtained by summing these spins from left to right. Okay? And this only gives you 2 to the h such spins. But if you want to continue, just continue this tree upwards. Okay? So when I run out of spins here, I got 2 to the h. I just say, well, this one that I thought was the root is actually the child of a new root. Put the new root here. Again, flip along this edge with probability epsilon, and you can extend the tree. So this way you can keep going. And then it's very easy to see that the variance of this process, if I go on this process, say, for time n, the variance doesn't grow like n. It grows like a larger power. So the standard deviation doesn't grow like root n. It grows like some power of n that's close to 1, depending on how close epsilon is to 0. That's easy to see. To check the unpredictability property, well, if you think about it, it's close to a local CLT. So the proof is also close to proofs of local CLTs, namely analyzing the Fourier transform. And you can look in the original paper, also in my St. Floor notes, probability on trees and introductory climb. This Fourier transform calculation is included. Okay, so that's what I wanted to tell about that story. And in the last 15 minutes, I want to tell you another kind of very recent but story that I find quite exciting. This is joint work with Babichenko, Yakov Babichenko, Ron Peretz, Perla Susi, Peter Winkler. It's a cop and robber problem where initially we thought that these unpredictable paths would be crucial. Later we realized that the simple, or some of the co-authors realized that the simple unpredictable paths, so the simple paths that spread out are actually what you want to use. So what is the story here? So before I shift gears to that, any questions so far? I'm going to. So I wanted to tell you this story about the unpredictable paths because there are several other applications of these. One beautiful one found by Alan Sly, another in joint work with Noam Berger. I don't have time to relate these, but it turns out to be useful to know about these paths. Yes? Yes?
One particular construction of unpredictable paths.
Yes?
One which refinements of that.
Yes. So again, they had several variants, but one variant is you use this, but you change epsilon as you go down the tree carefully. It converges towards 0. And by changing the epsilon suitably, they can get as good unpredictable process as there exist. Okay? No. I said in their paper there is another one. Okay. Yes. I mean, you can. It depends on the tail behavior of the sum, the exact theta. But the moment it's summable, then you get some theta. So you can calculate it from the tail of the.
What you said very quickly seemed to give arbitrarily small theta, which can't be true.
No, it's not arbitrarily small because you see. So I looked at the tail behavior. I said, jump 100 steps to the future, and then the tail is small. But in those 100 steps, you could get a lot of intersections. So, okay. So again, in the last 13 minutes, cop and robber problem. So we have. So the cop and the robber are moving on a cycle with n nodes. They don't see each other at all. The cop is moving nearest neighbor, so he can move left one, right one, or stay in place. The robber can move in big jumps, go wherever he likes in every step. Okay? And the game ends when they happen to choose the same node. So each step, they both choose a node to go to, but the cop is very restricted, only nearest neighbor. The robber can go anywhere. Okay? And the game ends when they happen to choose the same node. And the question is, if they both play optimally, what is the expected capture time? So when they play optimally, they should both be using some randomized strategies. And under these optimal randomized strategies, what is the expected capture time? You could view this as a zero-sum game, where at the end of the game, the cop pays the robber how long it took to capture. And so in a zero-sum game like that, you have there is a well-defined value of the game, which is what they'll get if they both play optimally. So, and the basic question we start out with is, can the cop catch the robber in linear time in order n? And let's really focus on that. So let's focus on what's the probability of capture in n moves. Is it positive, or is it going to 0 with n? Any opinions? What would you do as the cop or as the robber? initially we thought that a good strategy for the COP is to choose a direction, go in that direction, and turn at every step with probability 1 over n, and then you switch to the other direction. We thought, well, this should catch the robber in linear time. But that turns out to be a bad strategy, and the robber can escape that for time n to the 3/2. So okay, so then afterwards we realized that a good strategy for the COP is to use one of these unpredictable paths, and but finally it turned out that the best strategy for the COP is to do something very simple. So basically the location of the COP at time t should be, a plus tb, say integer part, mod n, where ab are independent and uniform. So let's see, this pair is uniform in the unit square. So you choose a uniform. So, okay, I would need let me just correct this a little bit. So A right, so the starting position is uniform mod n. Yes.
So the Kaufman randomized starting?
Yes. Okay. But it doesn't matter. If he has a fixed starting position, then certainly in n steps he can arrive at a random point, and we're allowing him n steps because so it doesn't matter. Okay. So this turns out to be the good strategy, and I don't have time, but a simple second moment calculation. If you do Zn, if Zn is the number of collisions in the time interval 0n, then if you just, again, use the second moment inequality, you'll find that the probability of Zn positive it's again bigger than the first moment squared divided by the second moment. Now, because of the initial random location, the probability of collision at every fixed time is just 1 over n. So the first moment squared will just give you 1. What is the second moment? Well, given that they collide at time j, what's the chance they will collide at time j plus k? Well, it's easy to see it's order 1 over k, and so you'll get a sum here of 1 over k, so you'll get order log n here. So just a simple second moment calculation with a simple strategy yields this kind of bound. So I won't give maybe too much detail on that. Now, what's a good strategy for the robber? Any suggestions? What would you do as the robber? So going to a uniform place is not good because you'll fall on the COP at every time with probability 1 over n. So it's just a geometric thing after n steps. So I claim that the robber can escape for superlinear time, meaning the probability in a round of length n that he will be caught is little o of 1. And in fact, under the optimal strategy, it is constant over log n. So the true answer is that in order n steps, the capture probability is order 1 over log n, and the time to capture under optimal play is n log n. Now, the strategy for the robber is kind of nice. So So here is the cycle, so interpreted as the interval 0, n, but taken mod n. So identify n and 0. And look at the time-space diagram. So this is time. And so I want to say where the rubber should be at any step. So he starts at a uniform point. Where should it be next? Well, maybe here, then here, then here. How are these places going to be chosen? Well, think of this whole picture as part of Z2. Okay, so we have a Z2 lattice. And make the rubber do a random walk in Z2, so ignoring the direction of time, just he can do a simple random walk in Z2 until he reaches for the first time the next level. Okay? And continue this way. Oops. Okay, and so on. So each time so we record when the rubber reaches a new level, and that will be his new location at the next time. Okay? So this is the strategy for the rubber. So he looks at this time-space diagram, and he takes a random walk on it to decide his next location. What this random walk strategy has is a property that the probability that at time t plus k he will be at any prescribed location so if x minus RT is less than k, then this probability is bigger than constant over k. So suppose this is the location at time t, and now I look at time t plus k, and I ask, what is the chance that the rubber is in any of these locations? So this is time t plus k. Any location which is distance at most k from the original location has probability at least constant over k. So this is a simple calculation with two-dimensional walks. And once you get that, then you can finish because, again, if Zn is the number of collisions by time n, then the probability that Zn is positive is at most the expectation of Zn divided by the expectation of Z2n divided by the expectation of Z2n given Zn is positive. Right? So you can verify this by multiplying by the denominator. Now, so the top here is, and this is, when the rubber is applying this strategy, the cop can do any strategy he likes. Okay? And so here I get a 2. Now, what's the expected number of collisions by time 2n, given that there is a collision at time n? Well, given that there is a collision, or given that there is some collision, so again, so the probability that the rubber at time t plus k will be equal to the location of the cop, I'll call that S at time t plus k, given that RT equals ST and some additional history, this is, by that logic, at least constant over k. So summing this over k's, you'll get here a constant log n for the denominator. So the 2 is just because I had the 2n here. So at any time, so since the rubber starts at a random place, at any time the chance he will, at any specific time, the chance he collides with the cop is 1 over n. Okay, so we just sum the indicators. Okay, and in the final 1 minute, I want to mention that this problem has an exciting connection with the Kakeya problem. So the Kakeya problem involves finding a set in the plane that contains unit segments in all directions, In fact, you want to turn the unit segments. And this set should have little area as possible. And you can have such sets of area going to 0. What is the connection here? So I don't have much time, but so let's suppose that the COP is using the strategy I mentioned over there. So he just chooses A and B uniformly at random and applies this walk. And let's normalize the locations of the robber. So here is the location of the robber at time m. But now this is in 0, 1. So it's convenient to normalize by n the locations. And if this is the location of the robber at time m, how could he be captured? So let's do a diagram. This is a diagram. Here is the parameter A. Here is the parameter B for the COP strategy. And it turns out that there is some triangle here where if A and B fall in this triangle, then and only then will the robber be captured at this time. And this has slope minus n over m. This has slope minus n over m plus 1. Okay, so if time is very small, so here everything is normalized to 0, 1. So I'm going to also run time to 0, 1 and location to 0, 1. So if the time is very short, the only way the cop will catch the robber is if he starts right next to the location of the robber at this time. And if he has the full unit of time, then he has more chances. So it turns out in the normalized diagram, the way the cop can catch the robber is if he starts in this location. And that's when he will catch the robber, if the robber is here in this location. And so it turns out that the overall probability, so we have a bunch of these kind of triangles with different slopes. And the overall probability of the cop catching the robber using this strategy is just the union of the areas of these triangles. And it turns out that the slopes of these triangles vary through all possible slopes. So these triangles can be translated to just give you a slicing of a triangle that basically spans the whole unit square. So if this is the point 0, 1, this is the point I, and you look at this triangle, all these triangles, they can be translated to form this union. So although they don't contain all directions, they contain a positive fraction of directions, which is essentially good enough for a Kakeya set. So without really going through the details, I don't have time, it turns out that a good robber strategy, namely one where he will be captured in a round with probability going to 0, corresponds to a Kakeya set. And in fact, it's known that this type of Kakeya sets obtained by partitioning into n triangles, Schoenberg already proved decades ago that the best you could do is total area of 1 over log n. So this exactly corresponds to the optimal COP strategies, COP and robber strategies. And let me stop here. Yes.
So if there is a Kakeya set instructions to then maybe there should be a three-dimensional Kakeya.
I'd love to find that. So let's say, right, so there's a very rich and ongoing history of the Kakeya problem in higher dimensions and in finite fields, and I think it's exciting to have yet another way to think about these constructions in terms of these strategies. But to be honest, right now we just know how to relate it to the most classical two-dimensional setting. But that's one reason to present it here. Maybe someone has an idea to extend this connection. Yes?
Does it require the sharp
The sharp curve. So one place where it was used is in transients of wedges in Z3. So instead of asking for transients of all of Z3, percolation in all of Z3, you could do a part of Z3, so all the points x, y, z, where z is less than, say, some function of x. Okay, so you look at some function of x, and you can ask, how can this function grow so that the resulting part of Z3 is transient, and also that the percolation in the resulting wedge will also yield a transient cluster. So this is discussed in the Hegstrom-Mossel paper, and there, in order to get very close to the sharp behavior, you need to use the sharper predictability profiles. It turns out that still using that method has to lose a log compared to the truth. But so for establishing transients of percolation in wedges, in the end, one uses other tricks to remove the last logarithm. But there are 5 or 6 subsequent papers on this delicate issues. But certainly, already the Hegstrom-Mossel paper uses their construction to get wedges which are almost optimal in terms of having transient percolation clusters.
One last question.
They said the original reason for choosing these unpredictable paths was to find a better way to fill up space than simple random walk. So how do these fill up space?
Well, you can easily check that if you have a process that would be restricted to some neighborhood of the diagonal, so at time n, if the process could only get to distance n to the alpha, and it's an oriented process, then then its predictability profile would be at most n to the 2 alpha. So these processes, especially if you use the sharpest ones of Hegstrom and Mossel, they cannot stay too close to the diagonal. They have to basically fill up space. So to get enough room to be that unpredictable. Because if something is, so in particular, if something is as restricted as the random walk, namely it stays within a tube of root n around the diagonal, it would be as predictable as random walk. So random walk is as unpredictable as possible given that restriction that it has diffusive escape from the diagonal.
Random walk 0.5, 0.7, 0.8.
Yes, you can. So, I don't want to make precise fractal definitions, but just say the interval over which it is spread should be larger than square root.